Say hello to the most incredible and complex space observatory in history, the James Webb Space Telescope. With 100 times the observational power of the Hubble Space Telescope, Webb can peer more than 13 billion years back in time. Due for launch this Halloween, Webb promises to help solve some of the greatest mysteries in the universe. I'm very excited today to be talking to Heidi Hammel, who's the Vice President of the Association of Universities for Research in Astronomy, as well as Matt Mountain, who is the President of that association. Thank you so much for coming on the show to talk to us.
It's a pleasure to be here.
It's a great pleasure to be here. We always like to talk about our coolest telescope too.
Well, speaking of the coolest telescope, James Webb Space Telescope, I'm sure it will be no surprise to you that, when I interview space scientists of fields as disparate as exoplanet research in our own galaxy and, the cosmic horizon of the early universe, I ask them what they're looking forward to, and they almost always say James Webb Space Telescope. It is definitely a highly anticipated project, and it's going to be very exciting once it's launched, hopefully later this year. If we could just begin by, an overview of why this telescope is so important and what's new about it.
James Webb Space Telescope is a new kind of telescope. It's going to be focused on the infrared part of the spectrum. So it's not quite a successor to Hubble. It goes beyond Hubble, and it complements what Hubble will do. When I talk about it, I usually say there's three things about it that are super special. One, is a lot bigger than Hubble. The mirror itself, composed of segments, is about 6.5 meters across compared to Hubble's 2 meters. So it's bigger than Hubble. It's colder than Hubble. And that's important. And when we joke a lot about how cool it is, it's cool not just because it's a cool science thing, but it's literally going to be a cool telescope because it's designed to look for infrared heat from the universe. The heat from the very first galaxies and stars that formed. It works in the thermal part of the spectrum. Hubble works at visible, like what we see with our eyes. So it's bigger, it's cooler, and it's further than Hubble. Hubble's in a low Earth orbit. This telescope will be at the Sun-Earth Lagrange 2 point, which is about 1 million miles away. You can do a straight line from the sun to the Earth and go another 1 million miles. That's where we're going to be putting James Webb Space Telescope, mostly to keep it cool, to use big sunshades to block the sun, to block the warmth of the Earth and the warmth of the moon. And that coolness is what's going to allow us to explore the heat of objects throughout the whole universe.
So, the way to think about this is when we used the Hubble Space Telescope, we looked deeper and deeper and went further and further back and saw these amazing galaxies. And if you look at these very deep galactic fields that Hubble has taken, they get a bit more orange and a bit more red, and then they just sort of run out. And you go, oh, we've run out of galaxies? The answer is no, because the universe is expanding, it's pulling space apart. It stretches the wavelengths apart and moves it from the optical to the infrared. So James Webb was originally designed to capture those longer wavelengths, heat radiation, because that's where the earliest galaxies are sitting, because the universe is stretched so far, they're so far back, with the universe, the deeper you look, the further back in time you are looking. It's a time machine. So James Webb is the ultimate time machine. And so we're hoping it will reveal this whole class of galaxies that basically have vanished from view from the Hubble Space Telescope.
And could you kind of spell out explicitly why it needs to be so cold in order to capture that kind of light?
So it's roughly at minus 380 degrees Fahrenheit, so it's really cold. And because the signals from these very faint galaxies, and as we'll talk about, these exoplanets are very faint. And what normally happens if you're looking for heat, you've got to make sure the telescope itself isn't what you're seeing. You want to see the thing beyond the telescope. And so the things we look at are very faint. And in fact, just to give a sense of how little heat we can detect, we can actually detect the heat of a bumblebee on the surface of the moon, if you could have bumblebees on the surface of the moon. And that's how faint we're having to go. And if you're going that faint, if the telescope was warm, it would be like looking through a bright searchlight looking for something, and you want that light, the infrared light, to go away. Is you've got to cool the telescope. So the universe and these very faint objects are the thing you see, not the telescope itself.
So 2 points I want to make, though, is that we aren't actually going to be looking for bumblebees on the moon.
No,
we're not looking at the moon, all right? Because our sun shields are going to block the moon. But another thing about this extreme cold, everything about this telescope is designed to optimize it to sense this infrared light from distant galaxies and other objects in the universe. And so that's why this telescope looks a little bit different than classical telescopes. You know, for example, it's got this big golden mirror sitting out there in outer space. There's no tube that contains it like Hubble has. Hubble looks sort of like a bust, you know, it's the mirror is hidden inside. We don't have that on Webb because that tube and the supporting structure would be warm and we would overwhelm our light from those distant galaxies. Also, the reason it's gold is not because we want it to be expensive, but because gold has very specific emissivity properties that reflect this infrared light very, very well. And so that's why it's the shiny gold mirror that's sitting out there in space. And then the big sun shields are there to block the warmth from the sun and the moon and the earth. They aren't like a single layer, they're multiple layers, and each layer reduces the amount of warmth that gets transferred so that you have we call it, sometimes we talk about SPF sunscreen, right? Like we put 50 on, right? The SPF of those sun shield of Webb is about 1 million.
Right.
That's how much it cuts down on the warmth from the sun. So everything about this telescope is designed to optimize that infrared light.
But because it's so big, we've had to fold it up, right? And we can't launch it. And so we have to unfold this sunshade, which is the size of a tennis court, and gently pull it apart. And it's like 5 layers of space blanket. We've got to pull it apart 1 million miles away from here automatically. And then we unfold the telescope and with its gold coatings, and it looks out away from the Earth and the sun and the moon at this very cold part of the universe that we're trying to detect. So it's going to be a somewhat hair-raising operation as we start unfolding this telescope, since nobody's ever built a telescope this big before.
Yeah, certainly. And, you know, I want to pick up that thread, but also get back to some sort of space bee content, just because one of the things I love about the James Webb is how just aesthetically pleasing it is. These honeycomb, the little beryllium mirrors and things. And like you mentioned, this very magnificent sun shield and just the size of it, the complexity of it, it just looks so different. And I'm not throwing shade on Hubble, but Hubble looks like a regular space telescope around Earth, right? And this is just so unique. So could you tell us a little bit about the design process for this, the kind of challenges that had to be overcome in order to create something with these types of specifications?
Well, since Matt is Matt, you're project optical scientist. You take that.
I'm the telescope scientist, so I work on the telescope side originally.
Okay.
Yeah, it was you know, it was a very interesting process trying to come up with the final design and so forth. Because first of all, we realized it had to be bigger than it can fit in the rocket. And so the idea that we'd use these segments together, because we tried this on the ground with telescopes like the Keck telescope, which is a 10-meter telescope, and so we know segments can be made to work. Each segment, though, has to operate at this minus, 300 degrees Fahrenheit, right? Mm-hmm. So the first problem was, how do we make mirrors work at that temperature, but when we have to make them in room temperature? So we actually had to get the mirrors, polish them to the right shape and size to very high precision. You stretch the Webb right out across the whole mirror, by the way. If you imagine a 6.5 meter stretched across the Atlantic Ocean, the largest wave that we allowed is roughly about 1 inch. That's how smooth the final mirror has to be. So how do you do that was actually the problem. And so it started by looking at the individual segments where you polish them all up, and then you do crazy things. You cool it all down and it distorts a bit. You measure how much it distorts, and then you polish the inverse distortion in. So when you cool it again, it will bend to exactly the right shape. And the first time we heard about this, I said, okay, this is a little crazy. But because we use beryllium, it works really well. And so it's called cryopolishing. We basically polish in the distortions. So as it cools, it bends into exactly the right shape. And then we'll unfold all these mirrors. And then each mirror has a little actuator. So we'll adjust them in space to get them just about right. We'll look at some stars and we'll line them again and then tweak each little actuator till eventually we get this incredibly smooth mirror surface, which is equivalent to having a wave no more than an inch across the Atlantic Ocean.
So we're going to make sure that we don't have a repeat of the Hubble issue where that was a single monolithic mirror.
Yeah.
And when it launched, its shape was what it was.
We can adjust the shape.
We can adjust the shape of JWST. So, this complex process that Matt has described gets us to, we think, as good as we can do, but we still have that final capability of being able to adjust in real time. Yeah. And so that gives us a lot of confidence in how we're going to be able to make this work and not have
a lot of confidence.
That is really clever. I love the way that you approach that challenge. I mean, that's just fascinating, and the helpful metaphor of the Atlantic Ocean really makes it the mind-boggling sophistication of it.
Yeah.
Yeah, absolutely. So when it launches, what's going to happen in terms of it getting to the Lagrange point, and how long will that process of unfurling it into its final form will that take?
Well, Heidi knows that when they first put the Curiosity rover on Mars, they talked about the 7 minutes of terror. Because just we're unfortunately into about 3 or 4 weeks of terror, because we've got to unfold this thing as it flies out. It gets launched, the cowlings all fall off. It starts going out to this L2 point. And as we do that, we've got to then unfold the sunshade and bring that out. The problem is, once you've got the sunshade out, guess what happens? It starts cooling really quickly. So now we've got to start unfolding the telescope, pulling out the secondary, getting all the optics lined up, and then start up the instruments. But the way I wave my hands, it's going to take 2 to 3 weeks to get that done properly.
We have a very complex plan for how this is going to happen. And there are, stop points along the way where you evaluate, is everything according to plan? If so, we move to the next step. If so, then we move to the next step. One thing I wanted to share with listeners is that this telescope, like Matt said, takes a couple of weeks to get through that whole unfurling and opening and getting ready for science. But even then, we have a lot of brand new pieces of equipment, cameras, spectrographs, and we have a very complex choreography of how we turn certain instruments in certain modes on at certain times.
In the right order.
In the right order, exactly, because some of the instruments are used for the pointing and tracking of things, and other instruments are not. So things have to be done in the right order. And the bottom line here is that once we go through that, we have to make sure all the proper modes are working. My takeaway is that we're not going to launch this thing and then next week have pictures for the public, or even next month have pictures for the public. It's probably going to be closer to 6 months before we have gone through all of these checkouts and verifications that everything is working fine before we really start executing the science programs that Matt and I and the other team members have devised.
So, not that we're superstitious, but they all have to operate flawlessly for this mission to work. And that's why we've done so much testing on the ground to try to make sure that happens, because it's a one shot. We have to get this right once. That's it.
So it's fair to say for a couple months after the launch, there may be among the James Webb team some elevated pulse rates, some vital signs that are a little bit like more attuned to the
That's a very true statement. Yes,
absolutely.
Watching carefully. and then as a big team, everybody's going to be looking over everybody's shoulders, because none of us can afford to make any mistakes.
Yeah, absolutely.
But it's a well-trained team. A lot of work has gone into plan this. We do rehearsals. We are rehearsing in virtual space how to do this at the moment.
That's right. And we even rehearse things that might go wrong so that everybody's ready for that. Not that anything will go wrong, but we just want to be on top of things. So there have been a lot of rehearsals going on. We really try to think this all through ahead of time, think of all the possible things to be prepared for whatever would happen.
Matt, since you're a specialist on the exoplanet side, I'd love to know how James Webb can tell us more about these worlds that are orbiting other stars.
So, James Webb was not designed to do this originally. And it has just fallen in our lap. We didn't even know there were many exoplanets when James Webb was first conceived. But because it's so stable, because it looks at the infrared and it's so big, we've realized that if you imagine this is the sun and a planet moves in front of it, we'll be able to see the little ring of atmosphere shining through. And by looking at the light before the planet goes through and after, taking the difference, we'll actually see what's in the atmosphere of these exoplanets, assuming things are lined up properly. There's a whole group of people really interested in this. Interestingly enough, it's a real shift, and Heidi's very aware of this. The guys who started James Webb look much more like me, rather grayer, male. The people who are actually leading this exoplanet science look much more like you. There's a real shift in demographic where there's a bunch of women leaders coming out and becoming real leaders in the field. And so we're seeing our field change with the Webb and because of the science. And that's really quite exciting to see that. The old white guys are having to hand over to a much more diverse, much broader scientific community to lead in this exoplanet era. And so that's actually pretty exciting too.
It's been fun for me to watch that as a woman in science, as an older generation woman in science. My background is both astrophysics and also planetary science. And when I started doing astronomy, planetary science, 30 years ago, that was a new field. We were exploring the solar system for the first time. And so we saw the beginnings of demographic shift that Matt's talking about, where far more women were coming into the field of planetary science because it was brand new and you didn't have any of the old structures. And now it's fun to see that same shift continue, but more focused on the astrophysical community as this whole brand new field of exoplanets opens up. And there's just so many opportunities. It's wonderful to watch that change.
So it's not only a diversity of worlds that we're finding, we're also including many more people into the study of that. And that's just fantastic.